Have you ever wondered how a computer can solve a Sudoku puzzle faster than you can even blink? Or, how an airline schedules thousands of flights without a single conflict? Well, it's not magic. It's actually a brilliant way of thinking called constraint satisfaction. So today, we're going to dive into how we can actually teach computers to solve these incredibly complex puzzles. Let's just start with a super simple analogy. Look at this kid's toy, right? You've got different shapes. Those are your decisions. You've got the holes. Those are all your options. And then you have one very simple, very strict rule. The star has to go in the star-shaped hole. And it turns out the world is just full of puzzles exactly like this, just with a few more moving parts.
So the big question is, how do we take that simple logic, shape, hole, rule, and teach a computer how to apply it to problems that are way, way more complex than a little wooden toy?
Well, to do that, we've got to learn the official rules of the game. This is what people in computer science call a constraint satisfaction problem, or just CSP for short. Here's the cool part. Every single one of these puzzles, I don't care how complicated it looks, can be broken down into just 3 core components. You've got your variables, your domains, and your constraints. So let's break down what each of those actually means. Okay, first up, variables. These are just the unknowns, the questions you need to answer. In our toy puzzle, the variables are the different shapes we need to place. In a Sudoku, it's each one of those 81 empty squares. They're basically the whats of the problem. All right, next, every single variable has a domain. Think of this as the pool of possible answers for that variable. For our little shapes, the domain is the set of holes they could potentially fit into. For a Sudoku cell, the domain is just the numbers 1 through 9. Simple enough. And this is where the magic happens, the constraints. These are the rules of the game. They are the logic that connects all the variables together and tells you which combinations are allowed and which ones aren't. The most basic constraint for our toy is that the shape of the block has to match the shape of the hole. That's the rule that makes the puzzle, well, a puzzle.
So the ultimate goal here is to find what we call a complete and consistent assignment. Now, complete just means every variable gets a value, every shape is in a hole, and consistent means none of the rules, none of the constraints are broken. Sounds pretty simple, right?
Okay, all this theory is great, but let's make it way more concrete. We're going to use a classic example that really brings these ideas to life. So here's the puzzle. We've got a simple map, and our job is to color it in. But there's one rule. No 2 regions that touch each other can have the same color. This is a perfect textbook example of a constraint satisfaction problem. So let's break it down. What are our variables here? You got it. It's the 6 different regions on the map. Each one, from R1 all the way to R6, is a variable that needs a value. In this case, that value is a color. And what's our domain? Well, it's the palette of colors we're allowed to use. For this problem, we just have 3 options for each region, red, green, or blue. That's the domain for every single one of our variables. Now, here's a really clever way to visualize the constraints. It's called a constraint graph. Each region is a dot, or a node, and we just draw a line between any 2 regions that touch on the map. Each one of those lines represents a rule. So that line between R1 and R2 literally just means the color of R1 cannot equal the color of R2. The computer's job is to find a coloring that doesn't break any of these lines. Okay, so coloring maps is fun and all, but this framework is incredibly powerful. Let's take a look at how it applies to solving massive, real-world problems that you probably deal with every single day. So computers can attack these problems in 2 main ways. The first is incremental, which is kind of like building a solution step by step. Think of the 8 queens chess puzzle. You place one queen, check the rules, place the next, check the rules, and so on. The other way is to look at a complete, finished solution, like a totally filled-out Sudoku quid, and just check if the whole thing follows all the rules at once. And this right here shows you just how versatile this way of thinking is. Scheduling classes at a university, the classes are the variables, the time slots and rooms are the domain, and the constraints are things like no instructor can be in 2 places at once. Sudoku, the cells are the variables, numbers 1 to 9 are the domain, and the constraints are those classic no-repeat rules. Even something like package delivery logistics is just a massive CSP in disguise. So why is this so revolutionary? Why is this way of thinking about problems such a game changer? Well, it all comes down to the power of using those constraints to be really, really smart about how you search for an answer. And this is the key takeaway.
Instead of just brute forcing a solution, trying every single possible combination of colors on the map, which would take an eternity, a CSP solver is smart. The second it makes a choice that breaks a rule, it immediately backtracks and just cuts off that entire branch of possibilities. It doesn't waste any time exploring dead ends.
I absolutely love this way of thinking about it. Solving a CSP isn't about that frustrating search for one tiny needle in a giant haystack. It's about intelligently and efficiently getting rid of all the hay so that the needle is all that's left. And that really leaves us with a final thought. This isn't just for computers. I mean, when you think about it, planning a group trip or organizing a big project, that's its own kind of puzzle, right? So what problems in your own life could you solve a little easier if you just took a second to clearly define the variables, the options, and most importantly, the rules of the game?